Hello everybody and welcome back to another video on my channel. Today we will be talking about the part 2 of friction, or some of the more theoretical aspects of friction. Now, in part 1 we talked about more of the practical aspects of friction and how most of the problems you will encounter can be solved using those techniques. But just because this video is about more theoretical aspects of friction does not mean that you can't use it to solve problems. In fact, these theoretical aspects become even more important than the other practical aspects when you go up in difficulty to competition level physics, and sometimes you are forced to derive formulas with variables instead of being given values. So, I think that's about it right now. So let's move on to the video. Now, as I said, this video is about theoretical aspects of friction. But the first place and the best place to start when discussing these applications or concepts is, what even is friction? Now, there are two main definitions of frictions. One that would probably be more of a mechanics definition, and one that would be thought of more of a chemical physics question or definition, or some sort of more advanced or molecular definition of friction. Now, I'm going to start with molecular definition, as I'd rather introduce you the mechanics definition a little later, so it stays fresher in your brain when we discuss more aspects about that mechanical definition of friction. So, let me introduce you to the molecular definition of friction. So, what happens is, let's draw a floor and a box. Now, this box, we'll have it moving along this floor. Okay? And now, let's zoom in to the molecular level. So over here, there's a bunch of particles or molecules in the floor, etc., etc. But when we have the box, this box is also made up of molecules. Let's do these a different color. So now that when these box particles move, they start brushing up against these particles. So tiny interaction happens, which is signified by these tiny arrows that I'm drawing over here. Now these interactions cause a lot of energy and heat, energy, etc. But they also cause some force against the direction of motion, especially since when the particles collide, they lose some of their energy when they're not moving. So, since these particles collide and they release energy, and they lose a little bit of energy also. Because when we collide with other particles, conservation of momentum, which is a different topic we will discuss, or just generally conserving energy, which is a fundamental law of this universe, says that energy can't be created or destroyed, and it can be only transferred. And the transfer is the kinetic energy from these molecules into the molecules in the floor. So in fact, that's why the floor molecules will start bouncing around themselves also a little more, and they will heat up just a little bit. Now, if this doesn't make as much sense to you, you'll probably make it more clear when I start explaining conservation of energy in more detail. But I think that's about all you need to know for the molecular definition of friction. But I said there was a second definition, and one that at least I think is a little more useful, which is the mechanical definition of friction. Now, again, like the chemical definition, let's draw a floor and a box. And this box is moving this way. Now, what happens is we have our force of weight going downwards, right? mg. But then, to make sure this isn't sinking into the ground or floating, we have a normal force. Now, this normal force is the vertical component of something we call contact force, which is the force made when there's motion or when there's two objects in contact with one another. Now, where does friction come into all of this, you might ask? Now, if you watched my last video, you might remember that our friction formula, force of friction, is the coefficient of friction times the normal force. Now, as we'll see later, this coefficient of friction will have a different meaning down the line, but you should know that since this is related to the normal force, and this sort of forms a right angle like over here, and we have the normal force and we know friction is horizontal, friction is actually the horizontal force of this contact force, and we'll call the contact force C. But friction is the horizontal component of this contact force. So that's actually the real definition of friction in terms of mechanics. Now this contact force is actually also comes from this molecular definition, as the molecules are also moving up and down, but connecting them requires some more advanced physics that has not been covered and that I'm not completely sure of myself. So that's essentially how the mechanical and chemical or molecular definitions of friction work. So now we know that this is how it works, but how does the contact force work? Like, what else can we withdraw or what else can we realize from this contact force? Well, number one, let's draw a new diagram so I can explain this. And number two, look at the contact force over here and the normal force and our frictional force. We are going to assign an angle. This angle is theta. Now, you could of course assign the angle over here. This could be theta or theta 1 or theta 2, but it will basically work very similar. And oftentimes in physics, we will also be measuring angles from the vertical, just like we did in inclined planes. And many people find this to be a little more consistent and easier, as our derivation will involve using sine, cosine, and tan instead of sine, cosine, cosecant, secant, and cotangent. And those are slightly more complicated trig functions, and even though I'm pretty sure I expect you to know trig and they're still simple, it becomes harder to work with when we get into harder applications. So that's why we choose to have our angle from the vertical. So this vertical angle becomes that, theta, but our friction is micro n. So micro n and n, if we draw a right triangle over here with theta, n, and the coefficient of friction times n, with our contact force as a hypotenuse, by the Pythagorean theorem, we get the contact force is equal to n times the square root of coefficient of friction squared plus 1. So this is very, very, very useful, in fact. Now, while it might not be useful in more elementary physics, like something like honors physics or like early AP Physics 1, this will be much, much more important when we go into something like competition physics, like the F is equal to MA, or even the USA Physics Olympiad. So, since this is very important, what else can we learn from this? Well, we can learn that, of course, this depends on two forces, but an application of this, where I think you would be more clarity, is if we have a ramp, a force, and a tension pulling it in this direction. Now, this force, by Newton's third law, must have an equal and opposite force. So, we have this over here, our contact force, C. Now, by all other standards, you might think, wait, if it's an equal and opposite force, how is this gonna work? Like, what is this going to do? This doesn't make really any sense at all. But that will be explained in a short while. But before that, we realize that contact force is over here, and we have our normal force and our force of friction. Opposing this, with our angle to the vertical. So we can realize many more things, as this angle is also the same, as everything is along one line in using the vertical angles theorem. So, since we know that the angle is the same, we can find tension in terms of normal force, contact force, or even friction. So, that's just a very simple application of it. But what was I talking about earlier about how in reality this is okay? Because now let's move on to another example. Well, not really an example to solve like I do in my previous videos, but an example to show you how instead of just impeding motion and making Newton's third law look like it just stops all motion, friction is actually the reason that there's any motion at all. So, for this example, let's take the block, a horse, and the cart. So, let's draw the floor. We have our horse over here. I know, not a very good drawing. And never mind, that looks like a spring. We can't really do that. Let's just have our horse be over here. Well, or a human pulling the cart. That's also fine. So this cart will have wheels on the ground, and we are pulling it in this direction. Now, by all things, you might think, oh, Newton's law would make it go this way, and since every force has an equal and opposite reaction, that means that this force, it can't move, and that there's no motion. But let's examine these two things over here, these wheels, and what force they exhibit. Now, this force over here is horizontal, and that's vertical. But when we have friction, friction is against the direction of motion for now. Or is it? Because this has a downwards force over here, and this has a downwards force over here. But by contact force, we realize that when we're moving this way, and when friction is, in fact, like that, we have technically our kind of force of friction over here. So that makes the contact force in this angle, and the force of this object 1 being contacted with the second object, object 2. Notice how I said the order. Object 1 is putting this force on object 2. So that means there's going to be a same force in the opposite direction. So we have the force of 2 on 1. So let's put this as C21. Now this goes in the same direction as motion and upward, but it's counteracted by the weight. So there's still no vertical momentum. But you realize there's still horizontal motion. And that's true, because when we have our force of friction and our contact force, the floor is not going to move. So, since we know that the floor is not going to move, that leaves a net force of this force to the right, and that's how friction, in fact, is the reason motion happens. Pretty surprising, huh? Who would have thought that the force that everyone teaches that's against motion actually works with motion and is the reason there's motion? So, there you go. That's an explanation of how friction makes motion possible. But I was going to do one more thing, and I am going to do one more thing. So, what we have over here is we have this formula for contact force. The contact force is equal to N times micro squared plus 1 root. So, how does that work? Well, we showed how it's by the Pythagorean theorem. But, as you can see, contact force times the sine of that angle theta is equal to micro n, or the force of friction, and contact force times cosine of theta is equal to the normal force. But, what is theta exactly, and what is the coefficient of friction exactly? Now, as I explained in my last video, coefficient of friction is inherently a property that is shared between two surfaces depending on the type of molecules and the irregularities in the surface. where I'm talking about irregularities, where we have these kind of particles sticking up and interacting with those other particles, thus creating what I was showing as friction. But let's go on a little detour. Let's see what this angle means. So, what we have over here is we have a normal force and a normal force. So, what if we divide the frictional force by the normal force? Then we'll get the coefficient of friction. So, the coefficient of friction is equal to the frictional force over the normal force. But that's just the opposite over the adjacent. And that's just the tangent of our angle. Now this is huge. This shows that the contact force depends on the surface also. As, let's write it as this. Theta is equal to tangent inverse of our coefficient of friction. And since this coefficient of friction directly depends on the surface, this will also directly depend on the surface. Thus, that means our contact force also is a property of the surface. So, what have we really proved and derived in this entire video? Well, I showed you what friction is. I showed you what contact force is. And I showed you how friction helps motion and how contact force and everything derived from it is really just another derivation from a property of the surfaces. So, I hope you found those realizations very interesting and unique, and I hope that you learned something new from this video, or even if you didn't, you just enjoyed watching it. So if you enjoyed watching it, please make sure to like, subscribe, and hit that notification button for more videos just like this, and make sure to comment down below any suggestions, tips, or anything you have for this channel, as it could really help me and this channel a lot, as I can make this better for all of you. So, learn some new physics, learn something new, enjoy life. Thank you so much, see you in the next one, and bye-bye.